first video, we're gonna try and find the value of the limit as n goes to infinity of 1 plus 1 over n to the nth power. So, how do we go about tackling this? Well, I think it was Euler who did find the value of this, and I don't know how he did it, but I know that when I was presented with this problem, I know how this is how I went about solving it. So you'll see if we actually just, this is a limit, so we'll just try and actually plug in n equals infinity for this. We'll get 1 plus 1 over infinity to the infinitieth power, if you will forgive my notation using infinity. Well, what's 1 over infinity? This is just 0. So we're just going to get 1 to the infinity, and this is undefined. This is pretty much 0 over 0. So we have to do a bit more work to find this. Well, let's take a look at this and try and see if we can make this not just a function of n or a limit of n. There's a limit of n and a function of x. So where would we put the x in here? What if we just replace this 1 with an x here? We get the limit as n goes to infinity of x plus 1 over n to the n. All right, well, this doesn't work, because if we just do what we did over here, we just do the same thing we did over here. We just get x to the power of infinity, which is not helpful. Not helpful, because that's not gonna convert. It's either gonna converge to 0, converge to 1, or go out to infinity based on my knowledge. So what if we put the x in the exponent here? All right, what if we put that there next to the n? Well, that's not helpful, because that's just our original limit to the power of x. So that's not helpful. That's not going to help us. So let's just consider this, right? Well, what if we do this? 1 plus x over n to the n. And you get the limit. No, oops. I already wrote limit. As n goes to infinity. Is this going to be helpful? Well, let's take a look. Let's do what we did before, right? We plug in this infinity, and any x divided by infinity, or the limit as n goes to infinity, forgive me. Well, that's just going to be the same 1 to the infinity, which is pretty much 0 over 0, which is undefined. So this might actually be helpful. So we've come up with a function of x. We'll call it y of x is equal to the limit as n goes to infinity, 1 plus x over n to the nth power. So if we can evaluate this as a function and try and find some properties of this function, it might be useful in finding the value, because plugging in x equals 1 into our function, y of 1 will equal this original value, and it will actually give us the value of this original, the original question. So this is now this is the question we have to solve. So the first thing that came to my head, right? This is something that that we could try for this is to see what the derivative of this function is. So if we take the derivative, we're gonna get dy dx, and I'll use this notation. I like this. I like this notation rather than y prime. I just prefer it. It feels more natural to me. And of course, this is just going to be the limit this is just going to be the limit of the derivative. The derivative of the limit is the limit of the derivative. So we can just keep the limit out here as n goes to infinity. And let's just look at this. So of course the chain rule, we deal with the outer function first, the derivative of some number to the power of n. Well, that's just n times a number, which is 1 plus x over n, to the n minus 1. Okay, and then okay, that makes sense. And then we're going to multiply that by the derivative of the inside, because of the chain rule. And we are differentiating this with respect to x. So the derivative of 1 plus x over n, well, that's just a constant, so that just gets, we just cancel that out. And well, the derivative of x, well, 1 over n is just a constant. It's going to be x times 1 over n, and the derivative of x times a constant is just the constant. So it's going to be 1 over n. And what you notice is this and this cancel out. So what you get is dy dx equals the limit as n goes to infinity, 1 plus x over n to the n minus 1. So that's dy dx, and we know that dy dx is that. What you'll notice is that this n minus 1 is, in the limit, is negligible, right? If you imagine plugging in 1,000,000 into this function for n, you're gonna get a good approximation for what this actual limit is, but you're gonna get 1 plus x over 1,000,000 to the power of 999,999. So it's not going to change anything. So this is negligible. So you're just going to actually get the original function. You know, it's not going to change. 1 plus x, the limit as n goes to infinity, 1 plus x over n to the n, right? Because this is negligible. In the limit, it will be the same. And this just equals y. So we have, now we have a differential equation that we can use to solve this. And we get dy dx equals y. Okay? So now I know a lot of you are probably, you already see where this is going. Because of one very particular function that satisfies these properties. But let's actually go through this. Let's actually solve this differential equation, and it is separable, so we can do that. So we're just going to multiply both sides by x. So we got dy equals y dx, and then divide both sides by y. So we get 1 over y dy equals dx. Right, and then of course the next step in solving a differential equation like this is just integrating both sides. So we get, and what's the antiderivative of 1 over y? That's just ln y, of course, plus c, because the derivative of that constant is going to round down to 0, and that's equal to antiderivative of 1. That's just x with respect to x plus c. And of course, these are just arbitrary constants. So we can just actually write this as ln y equals x plus c. Of course, we can write this as c1, c2, c3, but I don't see a point in it because we know that it is just an arbitrary constant. So the next step here to find y is just undo ln y. So we raise e to the both sides, and then this cancels out, so we get y equals e to x plus c. Well, this is just equal to e to the x times e to the c, but this is just another arbitrary constant, so we can just say this is c to the x. So here we go. This is actually the value of our original function, right? So we know that the limit as n goes to infinity, 1 plus x over n to the nth power is equal to some constant, and we don't know this constant, e to the x. So that's interesting. That's nice. But what's the next step in finding this value of c? Well, we would just have to try some values of x. Right? We know this is equal to y of x. Well, what's gonna make this simple? Let's try y of 0. Let's try y of 0. So we know that y of 0 is going to equal c times e to the 0, which is e to the 0 is just 1, so this is going to equal to c. We also know this is going to equal the limit as n goes to infinity of 1 plus 0 over n, which is just 0. So we just cancel that to the n. And the limit as n goes to infinity of 1 to the n, that's just 1. So c equals 1. So in fact, this limit, this function of x is y of x, 1 plus x over n to the power of n, is actually just equal to e to the x. How great is that? Now, of course, we still have to plug in, right, the value of our original limit, right? Remembering that y of 1 is just going to equal this original limit. So we plug in 1 into this, and this will give us the limit as n goes to infinity, 1 plus 1, because that's x, over n to the n, equals e to the 1, which is just equal to e. So our original limit is equal to e. Thank you.